And let me check the recording volume. So it is recording. I always want to double check because I had done this a few times, like, thinking that it was recording and it was recording just the screen, but the audio was set to the wrong channel. So
all the
I have
important points are going.
Well, I mean, for this class, it's not that big of a deal because a lot of times I actually do things on the command line,
Right.
so it's not as big of a deal. All right, so let's go ahead and get started. We got two major things that we're going to do today. So let's go back and kind of recap, the last topic from the previous class. It was cisp versus RISC. You guys still remember that? Okay. So with cisp, which is complex instruction set computers, what the hardware manufacturer does, like in this case Intel, is try to pack more complexity into the silicon, into the processor. So they offer you, a lot of convenience. Like in one single instruction, you can do a lot of fancy stuff in assembly language, as opposed to RISC, which is reduced instruction set computer, where each instruction can really only do like this much. Okay, so in order to do something that's complex, you will have to do it in multiple instructions instead of one single instruction. So you might think, well, that's not so good because now we need multiple instructions just to do what the other computer can do with one single instruction. Well, that is true. Okay, so from the perspective of you guys who will be writing the programs in assembly language in this semester, the cisp approach may sound better. Okay, but it also brings some additional cost to not just the hardware but also in programming. In programming, now you have to learn all the different addressing modes instead of one. Okay, now you have like 14 of addressing modes that you have to remember, and then you have to pick the right one to use at the right time. Two, it is going to cost more in hardware because now you're packing more stuff onto silicon, so the die size increases. When the die size increases, the yield goes down and the cost goes up. Okay, and the worst part has to do with power efficiency. Because the more transistors you have on the processor, the more things are clocking, changing state at the same time. And as a result, the power consumption goes up. And when you look at how much computation you can perform on a per joules, which is a unit of energy basis, the cisp processors actually lose to RISC processors. In other words, if you look at how much energy it will take to, let's say, compute, let's say to crack an encryption key, okay? A RISC approach, even though it might take longer because the processor is weaker, it runs slower, but in the long run, it will take less energy to finish the job compared to a Intel Pentium processor. And that's the limitation right now. I mean, to you and I, it's not a big deal unless it's on a phone, on a desktop computer. Power consumption usually is not a big deal. But when you look at data centers, it is a big deal because the limiting factor right now, what is limiting how much processing power they can pack within a building, is not space. It is actually how fast they can extract heat. Yep.
Oh, never mind. You literally just answered my question.
Oh, okay.
Thank you.
Yep. And it actually makes sense to kind of relate it to what you guys can do is to imagine you have a LAN party. Okay? So you have a LAN party and everybody brings in a computer with two super duper graphics card in it. Okay? So every single computer they bring in is a 1 kilowatt rating computer. Okay? Not all the time, but the power supply has to be rated at 1 kilowatt. Okay, 1,000 watts. And now you have, let's say you put 4 people into a room, and the room is not that small. Let's say 12 by 12 foot, okay, which is a sizable room for 4 people to play games in. Okay, so when you combine the heat from the computers, from the people, from the monitor, the AC cannot keep up. Okay, there will be more BTUs than most air conditioners can get rid of in that room. I mean, if you look at the entire house, yeah, your house size, compressor or air conditioner can extract that much heat. But when you look at just one single room, if you just buy one of those room-sized air conditioner, it won't be able to keep up. Okay, so that's a miniature version of the problem that data centers are dealing with right now. is just heat extraction. How fast can you get all the heat out of the building so they can pack more computers and more computing equipment in the room? Okay, before that was not the limiting factor. Before it was power supply. Okay, how much power can you pump into a building? And now it is how fast can you extract the heat out of the building? So that's one little discussion that is related to what we are dealing with here. I also lied last time. I said that's the last time you'll see something, and now here's a new version of it. But this one is much better. I spent a lot of time on this one, and this one actually has the microcode engine done, and I have some basic instructions implemented as well. So we'll just take a really, really quick look at this. It's not a homework assignment, but it is. I think it might help you understand, instructions in assembly and in general what is happening inside the processor. So we'll go ahead and take a really quick look at this. And let's see, we go to downloads, and it's called text. We'll get all the zip files, unzip tech processor. And this time it is a folder, okay? It's not just a single file because it has multiple components. I'll show you guys what the components are and why there are so many different components. So let's go ahead and start off the logic sim and the file that contains the processor itself. It's TAC processor 4 this time. I keep changing the file name so that you can compare the new version versus the old version. You can see what kind of changes have been made. So this one is pretty much done as far as the hardware is concerned. In other words, if I am the one in charge of the silicon, that part is pretty much done. What is not done is the microcode. So the microcode part is not done yet. There's still a lot of work to do. But what you can probably see already is the number of pins has decreased. Whereas before we have a lot of dangling pins where you can toggle like a 0 and a 1. Now there are only there are only 2 pins left. One is the reset pin, which has to be external to the processor because somebody is going to say, hey, processor, hold yourself in the reset state until power is stable. So that has to be an external pin. And the other one is the clock pin, which is down here. So everything that had a clock associated with it, all those clocks are now brought into the system clock, the one single system clock that the mouse pointer is on right now. Okay. You can also see that the ROM here, this is the microcode ROM. It is read-only, but it contains all the steps that you need in order to execute instructions. So you can see that this one, okay, let me just zoom in so you can see a little bit better. Okay. So when you look at the microcode ROM, the output, the width of the ROM is now increased to 17 bits. Okay, I know it's a really kind of odd number. It has to do with I really need that many lines to control all the various stuff within the processor. Okay, when do I enable the ALU? When do I enable the output of the ALU? When do I clock the increment the program counter and so on and so forth. So that's why the width has increased. Which makes programming it not very easy because now I have to convert between base 2 and base 16 all the time, just so that I can specify the operations. I have a spreadsheet to help me with this. I'll show you that later. All of these lines go to various parts of the computer, and in order to load the microcode, you can now right-click on this and say load image. And there's one image here called mcc.rom, which is microcode. I cannot remember what the other C is. So, but this is the microcode ROM, which means it gives you all the steps. Okay, it has to be saved separately because it is not a part of the design itself, and this is also a component that will be changed frequently without changing the rest of the design. And that's not right. Let me just double check here. Edit content. That's not supposed to be all zeros. Do that one more time. Load image. mcc.rom. Nope, that's all zeros. Okay, and there's also a program that you can load in RAM. So to load the program in RAM, you go to load image again, and this time you specify load register memory, which is just one simple program. And this program has basically only 3 bytes. The 08 is not even a part of the program, okay? So this program has 2 instructions. The first instruction consists of these 2 bytes, and the second instruction is just 1 single byte, which is 20. So what type of instructions are we talking about here? That's where the spreadsheet comes in handy. So I have a spreadsheet that kind of help explain, how the bit patterns within the microcode engine. So let's go to the spreadsheet here. So go to user, downloads, text processor, and the spreadsheet has an extension of ODS because it's an open office type of document. So this is the spreadsheet. I can increase the font size just a little bit to show you, what it is. The columns correspond to bits. So this is bit 0 to bit 2 of the microcode engine ROM. This is bit 3 of the ROM. This is bit 4 of the ROM, and bit 5 of the ROM, and so on. So it goes from 0 all the way to 16 because we have 17 bits output coming from the microcode engine. And each bit can either be a 0 or 1, with the exception of the first item here, which is a combination of 3 bits. So this one is basically the combination of 3 bits. I have not even started to use the ALU yet, and that's why all the entries are just zeros, because nobody cares at this point about the ALU operation selection. When you look at the rows, these 3 rows combine to become what we call the fetch cycle of a processor. Its only job is to say, hey, program counter, connect yourself to the address bus of RAM, okay? And then go ahead and read that location, as indicated by the program counter, and put it into the instruction register. That's all it does, okay? And then the very last step, which is row 6 of the spreadsheet, is saying, okay, take the most significant 4 bits of the instruction and use that to index into the microcode table so that we can start to execute instructions or microcode instructions related to that particular instruction. Okay, it's just a table lookup to find out, okay, how do we perform steps that I usually do by hand in this class, and how to do it automatically here using the microcode engine. The microcode engine is just a macro. That's basically all it is to look up, okay, so instead of having tag to manually clock this first, set that pin to high, clock that one, turn this pin back to low, and so on, the microcode engine is doing that automatically. Are we still doing okay so far as the concept is concerned? Okay. So that's just for fetching the instruction. 0001 is, just 0001 in binary is the load instruction. So this corresponds to the most significant 4 bits of an instruction of 1 byte. So if the most significant 4 bits are 0001, it is the load instruction. What it does is it will load a constant from the instruction itself, which is actually stored in memory too, and it will put it into the register directly. So you can pick one of the 4 registers because we have a bank of register A to register D. And these are the 3 steps involved to basically increment the program counter, let it control the address bus again, go out to memory, specify a read operation, but this time the content that you're reading back, you're not going to use it to put it into the instruction register. This time you put it into a general register in the register bank. Okay, those are the steps that are performed here. And then the last one, this is the last instruction that I worked on. This one will store a register into a location that is indicated by possibly another register. So you use one of the registers to specify, okay, where am I supposed to store this content? And then use another register to specify the content to be stored at that location. Okay? So that's what the 3rd instruction is supposed to do. So these are closely related to what we have been talking about, okay? Because we have been talking about an immediate mode operand, which is a part of the instruction. I'm just going to copy this particular bit pattern into a register. That is 0001, the instruction corresponding to that one. And this one, I got the label wrong. It should have been 0010 because it's base 2. So that's the bit pattern of the most significant 4 bits of this particular instruction. Are we still doing okay so far with the general idea of what is going on here, what is about, what this spreadsheet is about? So you can see a lot of bits here are basically unused. Okay, you can see all the zeros, that are constantly like the entire row are zeros except for 1. But at the end here, I don't want to do all the base conversion by hand, so I use a equation, and you can see the equation. That's the equation. It's base 2 conversion. Okay, I'm taking the value of each column and just add it, multiply it by the power of 2, and then add it to the next column, and so on. Okay, that's all I'm doing here. It's just regular base conversion, and it comes up with a number. And the number is this one. This is a base 10 number. It is represented as a base 10 number. This is the base 16 representation of the same number. So the first one is supposed to be 11500, and for whatever reason, the emulator did not store that correctly here. So I'm going to fix it. So 11500. That's the first microcode specification to fetch an instruction. Are we still doing okay so far with this stuff here? Okay. So as we try to specify more instructions, what I need to do is to go back to the spreadsheet and basically just create more instructions using this particular method. So when time comes, we'll have to do the add instruction, do the subtract instruction, the compare instruction, and so on. And that's what we'll do here, is to specify those individual operations in terms of, we need to control the registers, get it ready to be written to, or we need to read from 2 registers to perform the computation, and we have to specify this operation inside the ALU, and so on and so forth. Are we doing okay so far with all this stuff? Okay. So I can actually run this program, just so you can see what it looks like when we run the program through a simulator like this. The only thing you have to do to run this program is to control the clock. That's all you need to do. Okay. If you need to reset the whole thing, you can click this reset here. But because reset is also, click the wrong button. But because reset is also connected to RAM, when you click the reset button, it will also reset the content of RAM to all zeros. So we tend not to do that unless we have to. And if you have to do that, you might want to right-click on the RAM module and save the image of the RAM to a file first, just so that you don't lose what you have already. Okay. So let's go ahead and give this a try. My monitor just went black, just went dead on me. But the projector is good, so I can still talk. I just have to look this way instead of looking into the monitor. Okay, so at this point, we can just kind of scroll down here and then use the clock pin. Let me see if I can just decrease the zoom a little bit. And that's a little bit better. Okay, so I can do the clock here. So when I do a clock from 0 to 1, it's causing some transition. You can see some of the lines turn into bright green, and some are still just regular green. And you can definitely see that this location is now selected. This is the opcode of the first instruction. In other words, this is the first thing that specifies what we're supposed to do. 10 specifies we're dealing with a load instruction. It is going to load a constant and immediate operand into a register. So the source is an immediate operand, which is a part of the instruction, and the destination is a register. And in this case, the opcode itself is taking 1 byte, so the next byte, this 47, is the operand. So we are effectively copying 47, which is a part of the instruction, into a register. The register is specified as a part of the instruction itself. So when you look at how an instruction is decoded, which is this one here, this is INSREG, which is instruction register, you can see how the output of this particular 8-bit register is split into basically 3 groups. One group, which is the most significant part, go through this path into the MUX, and then out of the MUX, it goes into the microcode counter. So this part basically says, okay, let's index into a part of the microcode ROM to start the execution of the microcode corresponding to this instruction. The other part is split into two portions here. One portion goes to specify one particular register. If you look into this part here, the comment says register selection 0, and the other one is register selection 1. So with every instruction, you can select up to 2 registers. In this case, only one is needed because we just need to copy a constant into one single register, but not 2 different registers. Is that okay so far? Okay. Now because the bit pattern, okay, let me just do another clock first. So do another clock, and it should load. Okay, not yet. One more clock, and it will load 10 into the instruction register. So let's do it one more time. But you can see the microcode counter here is already incrementing to 01 instead of 00. And do another clock here, and it loads the instruction, which is 10, into the instruction register. So now the instruction register has a content of 10. The one part is a hexadecimal number, so it really is specifying 0001 as a bit pattern. The other part, the lower 4 bits are 0000. So it is specifying register A in the register bank. So right now, the microcode engine is almost ready to execute the third step of the fetch cycle. The third step of the fetch cycle is kind of interesting. Okay, you can see which instruction is executing. This is the second instruction. So we are almost ready to execute the third one. And the moment I click the clock pin here, you will see that it will jump to location 10 in the ROM, because that's how the indexing works. Okay, I'm using the most significant 4 bits of the instruction itself to index into the microcode table. And they're all off by 16 bytes or 16 words. So that's why the next time I do a clock transition, you will see that this won't be 02 anymore, and it will go all the way to 10 in hexadecimal, which is 16 in decimal. Okay, one more clock. Here we go. And at this point, I am executing microcode specification that is specific to this instruction. Whereas before it is just fetching it, and just fetching the next instruction and decode it. Now that the instruction is decoded, it is going to execute the steps that are specific to this particular instruction. And that part has to do with addressing the RAM, go to location 01 in RAM, and copy the content, which is 47 here, to register A in the register bank. So if I click this through, you can also see the program counter is incremented as well. So if I keep clicking this, it will move on to the next instruction, and then the next one. And at any time, you can actually click on a particular line here to find out what is the content on that line at that moment. Okay. Now the third, you can also see that it switches back to 00, because the third step of the sequence of steps to perform is to go back to the fetch cycle for the next instruction. So every instruction cycle goes like this. Okay, it goes from the fetch stage, which is from 00 up to 02 in the microcode table, and then it will index into the appropriate entry within the table itself. It will execute the microcode corresponding to that particular instruction. The last instruction, or the last specification, is always going back to 00 in the microcode table, just so that we can now start all over with the next instruction. It will fetch the next instruction, decode it, and then execute all the steps associated with the next instruction. The second instruction, which is this one here, is 20, and that's the entire instruction. It doesn't need another byte for this instruction, because the way it does it is it will use one register to specify a location in RAM to store something, and then use another register to specify what I'm storing into that location. So 20 means the least significant bytes are 0000, right? I mean, a 0 in hexadecimal corresponds to 4 bits of 0. Is that part okay? because 16 is 2 to the power of 4. So one hexadecimal digit specifies 4 binary digits. So the 0 in hexadecimal specifies binary 0000, which also means I'm using register A for both purposes. I'm using register A both to control which location gets updated and also which register is supplying the content to update that location. They're both register A. And what do you think register A should have at this point as its content? 47, yeah, 47 in hexadecimal. So we are going to store the constant 47 in location also 47 because I'm using the same register in this case. I'm not going to go through all the details, but I can just kind of show you what happens when this instruction executes. So right now I'm going through the fetch cycle again. And as we go through the fetch cycle, the instruction register will get the instruction itself, which is 20. It will decode it, and then the third step will index into the appropriate starting point of that instruction, which is 20 as the address of the microcode ROM. So we'll go ahead and clock it. And now we go to location 20. This is the first step that is specific to that particular store instruction. And as we go through this step here, the first one basically selects, okay, let's make register A the output. No, I take it back. Yeah, it will make register A the output of the register bank, but it will put it into the indirect register first. So 47 will go into the indirect register, and then the second step is to store into that location. Okay, so we can look into the indirect register, which is down here. You can see it's now 47 because the mux, this particular mux here can select either to use the program counter or the indirect register to control the address bus. So now the address bus is controlled by the indirect register, and you can see it is already addressing location 47. But I am not specifying this is a write operation just yet, and there's no clock to actually make the write operation happen. And that's going to occur in the next instruction in microcode. So click, click, and one more time. And now it has written to the RAM here with 47. So location 47 now has a content of 47 because of that particular instruction. And this is as far as I got, with the microcoding of this particular processor architecture. It is a very simplistic view of what is happening inside an actual production processor, but all the steps are kind of analogous to what is really happening inside a complex processor. Is that okay so far? I mean, are you guys relating this to the operand and addressing nodes that we have been talking about? Because it has all of those already. It has register operand, it has immediate operand, and indirect operand also. Okay. So I'm giving you kind of like a microscopic view of what happens when an instruction executes, and also what does it mean when we say, oh, this is an indirect operand? Well, it simply means that one register specifies the location to be affected or to become the source of the operation, and then we can do whatever we want with the content at that location. The address itself is not being used for the calculation or the copying. It is the content at that location that is being used. All right. Any questions about this whole thing? No questions?
I have a question.
Yep.
You said before that you were using a 17-bit wide code, but it seems like you're not using pin number 11.
That is correct, because when I moved that thing around, it made a connection because of the moving, so I thought it was being used, and then later on I found out, hey, that's not being used, so I cut it off.
Okay.
So I could have gotten away with a 16-bit, output at this point.
I was curious if you were going to save it for some other part of the.
I'm pretty sure later on we'll have use for that bit, so I'm not gonna do anything about it. But this is the process. This is the process of making a processor. I mean, you have to design the architecture first, decide how many registers you want to use, decide what type of operation will be supported by the processor, and then you make your microcode engine. Now the microcode engine is really just something to tie everything together. So until you actually write the code for the microcode engine, Your processor really doesn't do a single thing. It's just saying, okay, I have a way to specify what to do with every single component inside the processor, but I don't know the sequence of doing it. So this part is actually programming. It is a part of programming because you are doing something to make use of the hardware. If I remember correctly, the Intel processor, or at least some of the Intel processors, actually allow you to upload new microcode after the chip is manufactured. You can look it up, microcode update of Intel processors. You can probably find something there. Okay, so that means if Intel finds a better way to implement a particular instruction, potentially there's a way to do a runtime fix or patch to make use of the update of the microcode programming, which is kind of cool. Okay. Are there any questions about what I have just demonstrated here? No questions. All right. Well, it is on the web, so you guys have access to it already from Moodle. If you have time, I think this is probably a good thing to kind of experiment with. Even though it's not a homework assignment at this point, I think it will help you understand the material of this class, and especially for those of you who want to become an electrical engineer or a computer engineer, you will see this again. Okay, because the final year project at Berkeley, as an EECS major, is the design of a processor. Not using a tool like this, they use Verilog, which is a text programming language, to specify the components and how they connect inside the processor. But nonetheless, you will see this again, in a much more complex, context. All right. How many people are planning to go into computer or electrical engineering? Okay, a few. Okay, so you guys will see this again. To me, it is fun. It is really a lot of fun. So we are moving on to topic 2, and now we're going to talk about your homework assignment. It's called Treasure One because it's like treasure hunting. So what we'll do is, I'll just kind of read through this and kind of show you the process, the steps to get you going with the homework assignment. I'm not going to do the homework assignment for you, but I will show you all the steps that you need to take, at least to get to that point. Okay, so you download this file first, and you have to somehow copy this to the virtual machine in a Linux environment. For those of you who are running Linux natively, you don't have to deal with that. But if you're running Linux in a virtual machine because you have a 64-bit Linux or you're using Windows, you will have to use WinSCP or FileZilla to copy this file over to the Linux side first. Okay, so on this computer, since I'm using Linux already, I don't need to do something like that. So you have to do everything using your homework account. In this class, I don't think we have. Did I talk about a homework account or something like that? I don't think so. So it would be the same thing as you. Did?
We made our own usernames, right?
Yeah,
That's
based on
what
your
you're
username.
talking
Yeah.
Okay.
Yeah. So it will be in the same account as the other homework assignment. And then you have to decompress the file. So to decompress the file, I'm just going to say that your user is the account here. So the first thing I do is I'll copy the file from my downloads folder. Oh, it's already in the downloads folder. So I'm going to copy this copy this tar file to the root directory. So I'm going to copy treasure1.tar.gz to my root directory. And I will change back to the root directory here. Double check to make sure that treasure1.tar.gz is here. Okay, so it is here. And then I'll just do an untar thing. To untar something, you say tar xzvf. It stands for extract gzip2 format verbose, and then you specify the file name, treasure1.tar.gz, and that's all you need to do to decompress the file into its folder.
You need a hyphen, or
you don't need a hyphen.
Oh, you don't?
Nope.
Oh.
Because it knows the first chunk of stuff are switches, so you don't need a dash to say that those are switches. Okay, so now it has created a folder called Treasure1, and inside Treasure1 there's treasure1.s, which is the source file, the starting point of your homework assignment. So let's go to Treasure1 as a folder, and then take a look at what is treasure1.s. Okay. And that's your program. Okay, I'm giving you some code to begin with, and also some instructions of what you can and what you cannot do. So what you can do is to specify, change the question marks to whatever you think they should be. You cannot change any other code. Okay, so your job is to only change the question mark to the appropriate operands, but you cannot change other instructions. You cannot add anything. You cannot delete anything or modify anything other than the question marks. In this particular homework assignment, you are allowed to use any type of operands. So as you feel it is appropriate, you can use immediate, you can use register, or indirect. Those are the three addressing modes, or the three types of operands we have talked about here. You cannot access memory that is not allocated or initialized by the .byte, .word, or .int constructs up here, and I'll just kind of briefly talk about what each one is using a separate program. This is also a .int, that is also a .int, and your program is here. There are three places where you have to specify the operand. This is the first place, this is the second place, and this is the last place. In the end, at this point, EBX as a 32-bit register should have the base 10 value of this number here. Okay. All right, so how are you going to get started with this program? Can you look at a base 10 number and immediately tell what the individual bits are inside that base 10 number? I cannot. I mean, some people may be able to. With simple base 10 numbers, I can, like 128, yeah, I can do that. But with this number, no. So the first thing you might want to do is to convert the base 10 representation to a representation that is friendly for you to work on this assignment. Okay? Because we are copying 32-bit, we're copying 16-bit, we're copying 8-bit, and so on and so forth. And you have to be copying from something that is already initialized. So the first thing you want to do is to say, okay, I want to know what this looks like as a 32-bit number in binary. Okay? Because the base 10 representation is not going to help you much. So you have to convert it into base 2 first. Base 2 is nice, but since all of the other lines up here are specified in hexadecimal because of the 0x prefix, so you might want to convert the base 10 number to hexadecimal also, okay, just so that you can match up what needs to be in EBX with whatever is already initialized in this particular program. Is that making any sense so far? Okay. Now, hexadecimal also has one big advantage, and this is an advantage over octal representation. 2 hexadecimal digits is 1 byte. 4 hexadecimal digits is a 16-bit number, and 8 of those becomes a 32-bit number. So it cuts off a very clean boundaries and byte boundaries. And that's why hexadecimal representation is particularly helpful with stuff like this. Are we still doing okay so far? Okay. So now is a good time to use another program to illustrate what is a .byte, what is a .word, what is a .int, and what is a .int doing here with a label on the other side. I mean, it's like, okay, so these are the things that you do need to know in order to get started with this homework assignment. So I'm not going to use this one for that type of illustration, so I'll start with a different program to illustrate all of those concepts. So I'll just put it here. We'll just do a example 1. Okay. So in example 1, I'm going to switch to the data section first, which means I'm dealing with stuff that can potentially be changed by the program. And I'll just have L1 as a generic label, and we'll have a .byte. I don't know. Let's say 0x AB, and then we have a .word here, 0x 1 2 3 4, and then we have a .long, 0x. I'll make this one a little bit tricky. I'll make this one, like 876. Okay. All right. And that's the entire program. The rest of the program is really just to make the compiler happy. So the program is not going to do anything. It's just going to exit right away. The important part of this program is what it is exactly at label L1? I mean, that's the big question. All right, so let's go ahead and assemble this program using gstabs -o ex1.o ex1.s, and then link the program. The executable is called ex1, and we use ex1.o, the object file, as the input to the linker. And now we go ahead and quote-unquote debug the program. But the point is, I'm not going to even run the program. Well, we'll go ahead and get it started and put a breakpoint on line 9, which is the first instruction. But other than that, we are not even going to execute the first instruction. My only interest is to find out, okay, how many bytes are actually allocated in this case, and what do they look like? A byte, a dot byte, is the allocation of 1 byte and have it initialized. So in this case, dot byte 0xab is going to allocate the space of exactly 1 byte and initialize that 1 byte to the content of AB in hexadecimal. Is that okay? So it's kind of like an initialized variable in C and C++, and it's global. And then the next line, on line 4, we have dot word 0x1234. 0x1234 is hexadecimal number 1234. Dot word means we want to allocate the space of a 16-bit number and have it initialized. So in this case, it will allocate 2 bytes and initialize those 2 bytes to represent 1234 in hexadecimal. Is that okay? So basically, the dot word is just twice as wide as a dot byte. It is just allocating more and initializing a wider chunk of memory. Dot long is the last one. Dot long is the same thing as a dot int. I should have used dot int instead, but they are really the same thing. Okay, so dot int and dot long are the same in the context of a 32-bit machine. So in this case, a dot long or a dot int is going to allocate 4 bytes at a time and initialize those 4 bytes to whatever constant you specify. So in this case, it's going to use 32 bits, 4 bytes, to represent 876 in hexadecimal. Okay. First question, how many bytes are actually allocated in this case? Not counting the instructions, just for the dot byte, dot word, and dot long. 7 bytes, exactly. Okay, the first one is 1 byte, the second one is 2 bytes, and then the last one is 4 bytes. Okay, so 4 bytes are allocated. The next question is, how are those bytes sequenced? In other words, if I am to write out the content of those 7 bytes, what are the content, what are the values of those 7 bytes starting at label L1? What do you think? The first byte is going to be AB, okay. The second byte is going to be number 34 because of the little endian convention, okay. Because 34 is the least significant byte of 1, 2, 3, 4, and the processor or the assembler is conforming to the little endian standard, which means the least significant byte is at the lowest address. So that means 34 as a byte is at a lower address than 1, 2. So the first byte is corresponding to the dot byte, which is AB. Second byte is 34, corresponding to the least significant byte of the dot word. The third byte is going to be the 1, 2, which is the most significant byte of the dot word. What about the fourth byte? 7, 6. And then the fifth byte? 0, 8. Very good. Okay, we keep having zeros, right? But we don't need any more bytes. Well, dot long says, we will use 32 bits to represent 876 in hexadecimal. So what do you think would be the 6th and also the 7th byte? 0, 0, and 0, 0. Okay, so that's the content of those bytes. That's the theory. Now we need to double check and make sure that really is the case. There's one particular command that you will find useful for this homework assignment. It's called the X command for examine memory content. With the X command, you can also do a help on X. The help is kind of terse. All it says is, you can use X followed by a slash, and then specify a format, and then give it an address to look into. But in this case, what is the address? First of all, what is the format? The format characters are octal, hex, decimal, unsigned, binary, float, address, instruction, character, string, and Z, which is 0 padded to the left for hexadecimal. So in this particular case, we can use X, which is hexadecimal, and then you can also control the width of each item that you're looking at. So in this case, you have a few choices here. You can look at items byte by byte. You can look at items half word by half word, and this is where the confusion comes in, because a half word is 16-bit and a word is 32-bit as far as GDB is concerned. So the assembler doesn't look at word the same way as GDB. The assembler says one word is 16-bit wide. GDB says 16-bit is called a half word, and 32-bit is called a word. So you just kind of have to remember this part here. There's a little bit of disconnect between the assembly programming language and GDB itself. Okay.
Whose fault is that?
Huh?
Whose fault is that?
It has to do with your GDB probably predates the 32-bit architecture,
Right.
or it is on an architecture where it was originally written for an architecture where a word is 32-bit to begin with. And if I had to fault someone, it's going to fault Intel. All right, so let's go ahead and specify a command to do this. So we specify x/, and then you can specify optionally a count. In other words, how many things am I looking at? You can, if you don't specify the account, it is by default 1. But in this case, I'm going to specify 7 things because we have 7 bytes to examine. I want to look at each one as a hexadecimal number, so I specify x to represent, to say use base 16 as a representation, and then each one is a byte long thing, so x specify a b. So this will specify. This is specifying I want to examine 7 bytes and print each one as a hexadecimal number. Then I have to specify the address. The address part is a little bit funky because I cannot just use L1. This is not going to work. Here, in this context, I have to use ampersand L1. It has to do with the disconnect between the assembler and the debugger because they don't understand L1 the same way. L1 is nothing more than really just a label representing an address. But in GDB, it wants to look at L1 as an integer, and that's why we need to use an ampersand to specify this as an address. But once we do that, we get back what we expected. Okay, AB is the first byte, corresponding to the dot byte AB line. The next 2 bytes, 3, 4 is the least significant byte, 1, 2 is the most significant byte of the dot word line in the source code of the program. The 4 bytes at the end correspond to 876 as a 32-bit number, and because we are using little endian, 76 being the least significant byte is the one that has the lowest address. Are there any questions about the display of the content here? Now, one thing you have to remember is in assembly language programming, there is no boundary. Okay, so that means I can load, I can use a move long instruction and copy from this byte all the way up to this byte and treat it as a 32-bit thing. That is perfectly okay. So let me show you what I mean by that. Okay. So let's quit from this one, and I'm going to extend the sample program just a little bit. So this time I'm going to move long $L1 plus, let's say L1 plus 1, plus 2, plus 2 is kind of more fun, so let's do plus 2, and put it into register EAX, and then in the next instruction I will copy indirect EAX into register EBX, so just so that we have one register to specify the address and the other one to specify the content. Okay. So now let's go ahead and reassemble the program, relink, and go into GDB again. But this time I do want to stop and actually execute the instructions step by step. So I run the program, it's now stopping on the first line. And let me single step it. What do you think is in EAX at this point? We just executed line 9, line 10 has not executed yet. What is in EAX at this point?
08. 08.
08? Not really. Okay, so
What's L1 plus 2?
that's the question. What is L1 plus 2? Okay, so the real question is, what exactly is this expression? What is it, computing? What is the result of this particular expression? So what you need to do is to go back to the program and say, okay, what exactly is L1? L1 is not AB. L1 is not the byte AB. L1 is the address of the byte AB. Okay, because it's a label. It is a bookmark in your book. Okay, so when I say flip to the page where it is bookmarked by your L1 as a bookmark, L1 is not the content on that page. It is really representing a location in your book. Okay, so it's more like a page number. The bookmark is more like a page number, and not the content on that page. So when I say L1, I'm actually referring to the page number. When I say L1 plus 2, I'm saying, oh, it's 2 pages after that bookmark. It is still a page number. Is that okay? So L1 plus 2 is actually an address in this case. So EAX at this point has an address that is 2 bytes after L1. And what is at that location? What is at the location of L1 plus 2?
1, 2.
It's the 1, 2, exactly. L1 plus 0 has AB, L1 plus 1 has 3, 4, L1 plus 2 has 1, 2. That's the, that's the byte at the location of L1 plus 2. Okay. So let's go ahead and take a look at the instruction that we are about to execute, and let's see if we can find out what this is going to do. Okay, we are copying 4 bytes, starting from the location indicated by EAX. And we know EAX now has the address of L1 plus 2, which is the address of the 1, 2 of the dot word in this case. So I'm going to start copying from that location, but because the because of the move instruction is a 32-bit move, it has to copy 4 bytes, not just 1. So it's going to start copying from that byte, and then 3 bytes after that also. So the question now is, what exactly is going to be copied into EBX? That really is the question. Okay, we know how we're starting, right? Yeah, we know it starts with this byte here. The next byte is the 76 because it is the least significant byte of the dot long. And then the next byte is going to be a 08, which is the second least significant byte of the dot long. But we need 1 more byte. Where's that 1 more byte? It's the second most significant byte, which is a 00. Okay, so to write it out, okay, I'm just going to write it out on the whiteboard. Well, I'll use a text editor so it's also captured here. Mouse pad. Go. All right. So what we're copying is the 1, 2 from the dot word, the 7, 6 from the next item, okay, because it does not respect boundaries between the dot long, dot word, and the dot byte. And then the next one is going to be the 08, and then the next one is the 00. This is 1/2 of the dot word. This is the least significant byte of the dot long, the second least significant byte of the dot long, and the second most significant byte of the dot long. So those 4 bytes are being copied. But when they're copied into a 32-bit register, once again we have to factor in least significant byte at the lowest address. In other words, in this case, 1, 2 is the one that is at the lowest address. It will be copied to the least significant byte of the register, EBX. So when you read out the 32-bit content of the register EBX, what would be the content of that register after the copy? We know the 4 bytes. The question is, how do we read those 4 bytes as a 32-bit number? Starting with a 0, exactly. So the 00 is the most significant byte of EBX after the copy instruction, after the move instruction. And then, so it should be 00, 08, 76, 12. That would be the content of EBX in hexadecimal. Is that okay? Let's double check. So we start with single stepping the program first. Oops, wrong window. So we start with single stepping first, and then we want to look at EBX in hexadecimal. And you can this is one way to do it. You can say print/x to mean your print in hexadecimal, and then use $EBX to say, okay, I want to look at register EBX in this case, and it is 87612. The 3 leading zeros are not printed. In other words, there are 2 zeros here and 1 more here. Those are leading zeros, and by default, when you specify printing something in hexadecimal, it does not print the leading zeros. If this is like, I'm not sure whether it will do this or not. Nope. Okay, let me see if print.
Yeah.
Oh.
Z option.
Huh? The Z option. Print Z. Yep, there we go. So are we doing okay so far with this particular sample program? Is that okay? All right. So this is a hint of what you need to do with your homework assignment. Okay, it's a little bit more than this, but this is like a good starting point. So a good starting point is to find out exactly what type of bytes are already allocated for you. Okay, what is the content of all those bytes that are available to you, and using the X command is a great tool to do that. Okay, second program. So here comes the second sample program that you will probably find useful too. So let's go ahead and take a look at the second sample program. And with this one, we have something similar to the first one. So we'll do something like this. So .int, remember .in and .long are really the same thing. So in this case, I'm just going back to .int here. So in this case, I have .int L1. And then we have L1 divide here. And as its content, let's make this one a little bit, kind of more obvious. Okay, so this one will start with 1, 2, 3, 4, A, B, C, D. Oops, I got .int here, and we'll put this one as .int L1 minus 4. Okay, that would be good enough. Switch back to the text section, the code section. This. Okay, so I'm going to start with a few instructions here. So I'll start with move long $L1 to register EAX, and we'll do about the same thing as last time. And this is a good starting point. So here's a sample program that has similar elements to your homework assignment, not exactly the same, but similar. Okay, and the first 2 instructions, are basically the same thing as what we had last time, except this one is actually simpler. So what do you think will be in EBX after the second instruction, after move long indirect EAX to EBX? What do you think will be in EBX? The first instruction copies the value L1 to EAX. Now the value L1, the label itself, is a page number. It is an address. So it's basically just copying the address of the first byte of the first .int into register EAX. The second instruction says use the content of EAX as an address. Go to that location and copy 4 bytes from that location to EBX. What are the 4 bytes at location L1? 1, 2, 3, 4, A, B, C, D. Okay, 32 bits. 32 bits. So as a result, EBX should end up with a value of exactly 1, 2, 3, 4, A, B, C, D in hexadecimal with this program. Is that part okay? Okay. Because the most confusing part is which part is the address and which part is the content. So that's the whole point of the exercise, is to help us kind of differentiate which one is which one. Okay, so let's go ahead and do this one first. So we'll assemble link and GDB program. And this time we'll just put a breakpoint on line 11 and then run the program. So right now EAX already has something, it already is initialized. And I claim that EAX now has the address of something, right? So let's double check and go ahead and say, okay, what is in EAX at this point? Okay? And you can check it too. I mean, now that we think that EAX has the address of 1234 ABCD as a 32-bit number, you can use the X command to double check and say, okay, are we really sure that that really is the case? Let's double check. So the way we double check it is to use the X command, and then we specify this time a 32-bit number, which is W. Unfortunately, it is not, it's not long or int. It is a word in the X command. And then we specify we want to print it out in hexadecimal using 8 digits. And then the address is the result of the previous command, $1. Okay? Because when you see $1 equals to 0x080 blah blah blah, that means from now on you can refer to this number or the result of this as just $1. So you can just say $1 and say, okay, I'm going to reuse the number, the result from a previous evaluation, which is really handy. Okay, and sure enough, we get back 1, 2, 3, 4 ABCD. That's the content at that location. Are we doing okay so far with this program at this point? Okay, so when I single step the program, which is executing this instruction, and it says go to the location indicated by EAX. But what is EAX? EAX is 804908B, and the content at that location is 1, 2, 3, 4 ABCD as a 32-bit content. So I can definitely expect EBX to have the content of 1, 2, 3, 4 ABCD at this point. It doesn't hurt to check. All right. Any questions after this step?
You might have gone over this already, but you use $1 and $2. Could you use $foo or whatever, or does it have to be 1?
It has to be 1 because in this case, it is representing the result of the first GDB command.
Okay.
So as you do additional printing or evaluation of expressions, you will see $2, $3, and so on. So now you can refer to all those previous results of GDB as well.
Okay, that makes sense.
It's basically just a local cache, if you will, of things that you have done already. So you can refer to the result of something that you have done already easily in this case. All right, so let's go ahead and change the program a little bit and make it even more related to your homework assignment. What if I change this to L1 plus 4? And add another line like this here. Okay, well, one thing at a time, right? One thing at a time. Let's look at the first instruction first. I'll turn on the line numbers. Okay, if you look at line 10, okay, what is the result of line 10? After line 10, EAX becomes the address of what in this program? It becomes the address of the line of .int L1 minus 4. That is correct. Okay. Now .int L1 minus 4. What does it do? I mean, that looks kind of completely different from everything else. If you look at this line here, it looks completely different from everything else because we are not giving it a constant, like 1, 2, 3, 4 ABCD or AB or so on, or something like that. It's an expression. L1 minus 4 is an expression. The question is, what is that expression? What is L1 minus 4? What is L1? L1 is a label of an address, right? So an address can be treated as a 32-bit number. It really is just the location of a byte, right? Which is just a number. So can I subtract 4 from a number, a 32-bit number? Absolutely. Yeah. So L1 minus 4 is just a 32-bit number. But that 32-bit number so happens to be an address. And that address is corresponding to 4 bytes before the label L1. What is 4 bytes before the label L1? Remember, L1 is just a bookmark. So I'm just asking you, what is 4 pages before that bookmark? It is it's that thing here, right? And that thing turns out to be another .int, another 32-bit that we have allocated and initialized in memory. But those 32-bit turns out to be just L1 itself. Okay? Alright, so let's go ahead and run this program and then see what happens, okay? But we do want to make some predictions first. So let's comment this program in order to kind of give us a hint of what it's doing. And this is something that you can do as well. I didn't specify in the homework assignment, but you can add comments to all the existing code. Okay, so that makes writing the program or tracking what you're doing a lot easier, because you can just kind of comment and say, okay, by this time, this register has this, and by this time this register has that, and so on. So that's exactly what I'm doing here. All right, so now we can say EAX is basically L1 plus 4, which is an address, okay? L1 plus 4 has the content of L1 minus 4. So after the second instruction, you know what? This needs to be EBX. There are 2 ways to do it. Let's change it to EAX here and change that back to EAX. Okay. So with this one, I'm dereferencing EAX. Okay. So in a way, this is kind of like saying EAX is dereference EAX. Use EAX as an address. Go there, grab whatever it's pointing at, and then come back and use that to update EAX itself. So in a way, it is just like dereferencing in C and C++. I'm just using a variable, a pointer, to go to a location, retrieve whatever is over there, and come back and change the pointer itself to become that content. Okay. But in the end, what is at location L1 plus 4? This is L1 plus 0, L1 plus 1, L1 plus 2, L1 plus 3, and L1 plus 4 all the way up to L1 plus 7 are here. So that turns out to be just L1 minus 4, which is another address. Are we still doing okay so far with this reasoning? Okay. Now that we know that EAX becomes L1 minus 4 after the second instruction, and this time I remember because I just almost knocked over the row sheet. So it's an accidental reminder to myself. It's like, okay, take row this time at least. Okay. So now we go back to this instruction here. What it is really doing is it's saying EBX is the destination. We are still using EAX as a pointer and dereferencing. So now the question is, what is at the location of L1 minus 4? Well, what is at location L1 minus 4 is L1. So this is just L1 itself. So after this entire sequence, after these 3 instructions, EBX should be the same as the value of L1, the label itself. Okay, it's a page number. Okay, go ahead.
So if it was possible to print the contents of L1, would it be just CD? Is that the bookmark you're talking about?
The content of those 4 bytes is going to be like 0A da 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 da. It's an address, so it's not something that I can predict when I'm just looking at the source code, because a lot of that depends on how I link the program and a few other things too. Okay, but it is going to be an address. All right, so let's go ahead and check this and see if this is what we are going to see. So let's go ahead and reassemble, relink, and GDB again. List the program. Put a breakpoint on the first line, which is line 10. Just run the program up to this point. So what I want to do is, once again, I want to dump out everything in memory first. But this time, I don't have to do it byte by byte, because this time I know everything is a .int. Okay, so there's no need for me to go byte by byte or word by word. So we can dump everything as 32-bit items. So we use examine here, and then we specify 4 things. Well, 4, 3, yeah, 4 things would be good. 4 things, each one is a word, because a word in examine is 32-bit, and we want to dump everything in hexadecimal and fill up all 8 digits. And the content, or where we are going, is going to be L1 minus 4, because that's the first location of the dot int. Here it shows the wrong result. Okay, it is wrong because it is misunderstanding what L1 is. So we have to cast this to a char pointer first. That would be correct. Because remember, L1 is understood as an integer, so ampersand L1 is understood as the address of an integer, as a 32-bit integer. When you perform arithmetic on a 32-bit integer pointer, then every time you add 1, it is actually adding 4. Every time you subtract 1, it's actually subtracting 4, because it goes by the size of the thing that it is pointing at. So in this case, I have to cast it to a char pointer first, then it is just a byte. Okay. So this is L1 minus 4. This is the content of L1 minus 4. This is the content at L1, and this is the content at L1 plus 4. Okay. Is that really corresponding to what you expect? Okay, let's double check. Okay, I'm going to use the notepad here to open the source code, and then we can look at the source code and look at the actual code side by side. This is treasure. Which folder am I in? Oh, wrong folder. Oh, I put it into the root folder. And we'll look at the source code. Okay. Nope, this is, it's not treasure 1. I want to look at example 2. ex2. There we go. All right. So let's arrange this so that we can see both the program and the examined result at the same time. Okay, first byte is dot int L1. So we want to look at this part of the code and look at this number here and say, does that look right to you? Well, maybe, maybe not. We don't know for sure. But one thing we know for sure is, there is this byte sequence here, okay, 1, 2, 3, 4, A, B, C, D at label L1, and we just find it over here. So this is at location label L1. What do you think L1 is supposed to be? This location, ending with 8, 9, is corresponding to these 4 bytes. So what do you think would be the address of these 4 bytes? It'll be a, now this is in hexadecimal, so after 9 we have A, B, C, D. Okay, so we are looking at 8D, blah, 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 8D as the address of the first byte of 1, 2, 3, 4, A, B, C, D. That turns out to be L1. Is that making any sense? So L1 in this particular case is exactly 804908D. Okay, that is L1 itself. Do you find that pattern anywhere within the output of the X command? The first entry. That's L1. It is the address. These 4 bytes is basically the address of these 4 bytes. Is that making any sense? Sort of? Okay. What about these guys over here? Well, that's L1 minus 4. See, if L1 is corresponding to the first byte of this particular 32-bit integer, what is L1 minus 4? Well, L1 minus 4 will put us back here, but what is the address of these bytes? That's the address, right? That's L1 minus 4, and we see L1 minus 4 over here because of the .int L1 minus 4 in the source code. Is that okay so far? I mean, is it clicking? I mean, are you guys connecting this to the homework assignment? All right. So if I do one more thing with this sample program, okay, because we just take it one step further to basically finish this off. If I take this one step further, and in this case I use EBX as an indirect register and put it back into EBX, what do you think would be the result? What is at label L1?
1, 2, 3, 4.
Yep. So we go full circle back to the content of at label L1. So let's double check, just run this program again and double check that. So we put a breakpoint on line 10 and we run the program, single step line 10 first, print /z $EAX, okay, and then we single step again, print /z $EAX again, another address, and then we do it one single step again, say print $Z $EBX in this case, and then one more time to finish this. Single step, print /z $EBX, and it's back to 1, 2, 3, 4 ABCD. All right. So this part is also connected to your homework assignment almost pretty much directly. Okay. So you kind of have to think about these options. The most important part is to understand what is in memory. When I say .int L1, how are those 4 bytes initialized? That really is the big question. And to understand the L1 itself is a page number, is an address. It is not the content at the address. Okay? That part is also very important. So when we say, put L1 minus 1 into a register with a $sign, that means we are copying an address into the register, not the content at that address into the register. Now, at that location, it might be another address, which is perfectly okay. Because the move L instruction doesn't really care what is at that location. It just says, okay, tell me where I must, okay, the move L instruction is just copying the content, just copying whatever you tell it to copy. If the first operand of move L has a $sign, it is exactly what you tell it to copy. That can be just an integer like 2 or 3. It can be an address, can be a calculation, can be the result of the calculation using an address like L1 minus 4. When you use indirect addressing, okay, in parentheses to specify EAX or EBX, it is simply saying use this register to tell you where to go and copy the content at that location. Okay. Now, what you're copying can be something like ABCD 1, 2, 3, 4, something that is easy to understand. It can also be an address itself. You don't really care. You're just going to go to you're going to go those 4 bytes and just copy those 4 bytes. That's all you're doing. Okay. Are there any questions at this point about this assignment? No questions? Okay. Nobody cares how long you have to do this homework assignment?
We'll have it by the end of the day. So we'll have it by the end of the day.
When
That
is
would be
the
nice.
assignment due?
Well, it is due on Thursday, October 9th at 7 p.m. No, the time is wrong. I always make it due like right before the class starts, so it'll be 9 a.m. I'm going to change that. But it will be due next Thursday. You have 1 week to work on it, and it's a weekend in between today's class and Tuesday. So my recommendation is to get started on this one as early as possible, okay? And that's actually what the lab session is really intended for, is for you guys to get started, to do the homework assignment in the lab so you can ask questions. But if you want to go home and work on this, that's fine, but do it before Tuesday, okay? Get started on Tuesday and try to get as far as you can on Tuesday. Then you can come back with questions, okay? I cannot answer questions directly with the homework assignment, but I can try to clarify the concepts that you need to understand to work on the homework assignment. Any other questions? Is anyone tying this to the early part of today's class where I used my processor to illustrate those few instructions?
Yeah.
You're starting to make that connection? Okay, very good. That's the intention of the early part of the discussion. All right, excellent. So we will have a about 10-minute break, and then I'll be in the lab. So for those of you who want to get a head start, you definitely want to be there so I can actually at least get you started with the virtual machine and all the other stuff too.